Welcome back. Last time we talked about models and how a GIS represents spatial data. I talked primarily about the vector data model, a little bit about the raster model. In this video I'm going to talk a little bit more about the raster model and then again recap both the vector and the raster models. What are the basics of the raster model? Well, a raster model simplifies and generalizes real entities into a grid structure that has cells. These cells have to be equally spaced and rectangular. Be nice if they're square, but they have to be rectangular at least. The raster model is better for continuous geographic features. So you can think about things that vary continuously through the landscape, temperature, precipitation, things like that. The raster model is going to be way better than the vector model to represent those things in terms of efficiency and accuracy and things like that. So the vector model is going to be better for the built world and the discrete world. The raster model is going to be better for the natural world. Okay, so we got a grid. The grid's made up of cells. In this case, the cell size is such that it's a square cell. Doesn't have to be. Your grid has some number of rows, n, some number of columns, m. So that's basically the raster data model. Each cell will be assigned one specific value. So everything inside of a cell is represented as a single value. So in this case, the bold cell that is in this depiction might have the value 7. So every place, every location within that cell has the value of 7. If that cell is 10 miles by 10 miles, everything inside of that 10 by 10 mile area is going to have a value of 7. Rows and columns don't have to be equal. You can have wide and short, or tall and skinny. And cell size doesn't have to be equal, but it needs to be rectangular. Okay, so how do we figure out where these cells are in the world? Well, we're going to do something that involves choosing an origin. I've chosen the lower left corner of the lower left cell. I might have chosen the center of the lower left cell, or the upper right corner, or the upper left corner. Depends upon the model you're using. And I specify cell size. So once I know an origin and a cell size, since it's regularly spaced, I can tell where any one of the cells in this grid are just by saying it's some number of rows and some other number of columns from the origin. So you just specify an offset, and that's how you know where the cell is. So if you've done any type of computing, you can see that this is going to be a really efficient model for doing computations, because the computer's just going to be able to crunch along row by row or column by column. And since everything is consistent and regularly spaced, it doesn't have to do a lot of special calculations to get to where it needs to get. Okay, so the vector model I talked about last time, points can represent something like house address. A point has 0 dimensions. We're not concerned necessarily about how big the house is, just where it's at. So we can represent house addresses as points. If we want to represent a transportation network, it's going to involve lines. And since it's a network, and I'll talk about this in a few weeks, a network has the extra feature of the lines being connected to each other. And so that's one of the properties of what's called topology. I'll talk a little bit more about that, but in a network the lines are connected to each other. Parcels can be represented by polygons, and the parcel size would be representative of the area, and so that's one of the measures, and your perimeter would be the distance around the parcel. Notice when you look at the vector representation that everything boils down to points. On the left you just have points. In the middle, on line features, you have points that are connected, and on the right, where you have polygon features, you have points that are connected, but the first and the last point are at exactly the same location. Raster model, for something that's like a point, the raster would assign the value of that point to a single cell. And so a single cell might represent a point in that grid, and all the other cells might not have any values at all because there are no points in those locations. A line is represented by cells of the same value that are adjacent to each other. And so you can see that line segment 11 is the cells that have a value of 11. Parcels, same kind of thing. A parcel, in this case, number 5, has pixels that are adjacent to each other with the value of 5. So you can see where the raster model is a little bit blocky and a little bit pixelated when it's trying to represent what would be discrete or vector data. So the raster model is going to be better for continuous data, vector model for discrete data. So how do we sum this up? This is a graphic representation of some aspect of the real world. Well, what aspects? It's the trees, the lake, it looks like some marsh or some swamp around the lake, and some streams. Vector model might say, let's model the trees as forest, let's draw a polygon around those trees and call that forest. So the vector model is going to say you're inside the forest or you're outside the forest. If you're inside that polygon, you're in the forest. The streams are lines, the lake is a polygon, and what the model is calling the marsh is also a polygon, but when you think about it, it's a polygon with a hole in it where the lake is, because that specific location is not going to be both the lake and the marsh, it's only going to be the marsh. So you can envision the marsh as being a yellow polygon with a hole in it. Here's what a raster is. This is a grid, and the grid is regularly spaced. There's a bunch of blue cells. Those blue cells have the same or equal value. That's probably going to represent water. It's not going to know that there's a difference between stream and lake. It's going to represent water as one cell color value. The forest is green. That's going to have a value that you're going to assign to green, and the marsh is yellow. So you can represent reality in vector or raster ways depending upon what it is you're interested in and what might work best in terms of processing the information. Next time, start talking about how do you assign locations to things, and it actually turns out to be kind of a complicated thing, but we need to be able to assign locations to this data that comes into the system in order to make it information. Otherwise, a polygon is just a polygon. If we don't know where the polygon is, it's data. We don't know anything about it, so we have to assign location to that. That's what georeferencing is about. Okay, so we've come to the end of the first week of videos now. We've covered quite a bit this week. Basic course overview, what is a system, what is an information system, a geographic information system, a data hierarchy, what's a model, and what are the models that we use in a GIS to represent reality. So keep those things stuck in your head, and also remember, if it makes a difference where, geography matters. Okay, I'll see you next week.